Hi, welcome to another practical session where we're learning spatial statistics and spatial econometrics with R. And today's topic is spatial regression, particularly linear spatial regression. My name is Saif Ali. And as we've been emphasizing in these practical sessions, our goal is to develop programming skills to do our spatial statistics tasks, spatial econometric tasks. However, the skill acquisition is based on solid, clear, and precise understanding of the theoretical principles of the subject, which you will gain from the theoretical lectures that you've been watching so far. And for today's session, these are the points that would be good to have a solid understanding of, because if we don't understand this, what will happen is that we can run an R command. It's just like running a command. You can type it in, you can download the data, run the command, you will get some results. And you can even maybe put those results in a paper or something, but in order to interpret those results, in order to gain insight from those results, and more importantly, in order to deepen our understanding of our research area, our study area, we will need to go beyond simply the R command to do something and see internally what's really going on. So in order to understand the skill-based material, the R code that we will discuss today, it would be good if we understand what is linear regression, what is ordinary least squares. This is something that you can gain fairly easily from a textbook or from other online lectures, and is kind of required background knowledge for this session. And then, of course, the classical assumptions that we make before we run ordinary least squares regression. And how spatial autocorrelation, how when we work with spatial data, how does that violate those assumptions? It would be nice to know why we need spatial regressions in the first place. Why do we need a different class of models to work with data which has spatial relationships, spatial autocorrelation, and spatial effects? And of course, we need to be familiar with the spatial models that have been covered in this course, the SLX, cross-regressive model, the spatial auto-regressive model, SAR, and the spatial error model. I've used some abbreviations here. You may find abbreviations that are slightly different if you read a different book or maybe read some papers. But these are the basic three simple spatial regression models that are commonly known. And we would like to have understood those fairly well and fairly deeply in order to appreciate the code that we'll work with today. That said, what should we already have done in terms of our programming? Well, we should be fairly comfortable with loading new libraries, working with R. We should be fairly comfortable with the interface. We should be able to learn new functions, new libraries by reading the help manuals. I hope that all of you have gained this level of proficiency in R by working through the material in this course so far. If you haven't, it would be nice if you could review some of the previous exercises and try and replicate the results that I have shown you. And of course, you should be comfortable by now working with spatial data. You should know what spatial data is, how is it different from regular tabular data, and what are the different operations that you can perform with spatial data, plotting it, computing variograms, etc., etc. So if all of that is in place, if some of it is not in place, I would highly recommend a brief review. You can pause this video right now, and I'll be right here. When you come back, you can go back and review some of the materials and then start off from this point onwards. That would really help you to acquire the skills in a more solid and firm, get a more firm grasp on the skills that we will discuss today. And what we will discuss today is we will again prepare some new spatial data for regression analysis. And this data is specially prepared to run regression models, so it's slightly different from the data that we used earlier, but it is data that pertains to groundwater levels, which you're familiar with by now. And so that'll be step one. Step two will be to build a weights matrix. And that term I hope should be familiar to you, because when we run spatial models, we need a matrix that tells you about the different neighborhood relationships in your data. And it encodes that information in a matrix form, which is called the weights matrix. So we will learn how to build this matrix using R commands. So I'm going to move forward. I'm hoping most of you are with me. If some of you have gone back to review the materials earlier, I'll see you on the other side. So we will do a review of spatial regression models, but we won't do it right now. Let me get into the code a little bit. Let me show you how to prepare the data, and I will come back to this slide, and we will review these models nearer the end of the session at the correct place. So we already know there are three basic models which we'll be working with. We won't actually run these models in this session. We will run them in the next session, but we will prepare. We will do all of the preparation that's necessary in order to run these models. And the preparation we will do in this session. So let's transition to our R window, in which we have a new file corresponding to the session 8. And this file is called R session 8 spatial regression part 1. And of course, we will share this code with you. So let's begin by loading our libraries. Now, you are familiar with most of these, but there are three new libraries that we haven't used so far, and they're called SPDEP, SPDEP, Spatial REG stands for Spatial Regression, which provides most of the code that we need to run our spatial regression models, and then RGOS, which has some additional code to help us prepare our spatial data. So we'll go ahead and load these libraries. So remember, if you want to run some code in R, you can just select it and press run, and it will load all of those libraries. So it seems that went well, and we've loaded our libraries. So we're going to be working with a new data set, which is called spatial-regression.csv. So let's get into this data. We now know how to load data from a CSV, and we load it into an object called spreg. And then let's examine it. Let's see what's inside. So it seems there's district-wise or block-wise data, in fact, station-wise. So you have district, block, and hydrograph station. Type of station, year. So you have data. This is data for the year 2015. Well ID, spatial coordinates, which is of course necessary. Otherwise, we wouldn't have spatial data. And then we have four variables called post-monsoon, RFL-TY, which stands for rainfall this year. So TY is this year. So that means, what is this year? This post-monsoon observation for groundwater level was made in post-monsoon of 2015. So that's close to the end of August or beginning of September in 2015. And rainfall this year means the rainfall received around that particular well in 2015 in the months from June to September. So the monsoon rainfall that occurred right before the observation was made. And similarly, there's temperature this year, temp TY, and this was the mean temperature in May, April and May of 2015. So, and then we have percentage cropped area, LY. So LY stands for last year. So we have the percentage of cropped of area around a given well where an observation was made. What percentage of that area was used for cropping? That's what we have here. And this is last year. So this would be for year 2014. So remember that the cropping year begins in around May. And so from May 2014 to May 2015, is the cropping year. So this variable will encompass all the cropping that occurred between 2014 May and May 2015. And because, of course, we don't want cropping this year, because if you take cropping in 2015, then you're accounting for cropping that occurs after the observation for groundwater level was made. And that doesn't make any sense. If we want to regress groundwater levels and we want to see what factors influenced or were associated with that groundwater level, then the cropping of the future is not necessarily something that that if groundwater level is the dependent variable, then the cropping of the future as the independent variable doesn't really make sense. So we have taken cropping of the past and rainfall of the immediate past and temperature of the immediate past. I hope that's clear. So let me just show you this in a better view here. By clicking this, we can see our data and these 4 variables. So what we want to do is we want to understand how this year's rainfall, how much rainfall was received in some neighborhood of a well, how hot the summer was, and how much cropping went on in a period of 1 year, how those 3 factors influence the groundwater level observation made at a particular well. And of course, we'll aggregate this data to a sub-district unit. So we will not do it well-wise, but that is the data that we have. We have a dependent variable called post-monsoon, and we have 3 explanatory variables, and we want to run a regression to understand the relationship between the explanatory variables and the dependent variable. So that's the scope of what we want to do. So now that we've loaded our data, of course, we have to convert it into spatial data, which is done by using the coordinates command. So let's do that. So now we have SPReg, which was just a regular data frame, has turned into a spatial point data frame. So let's load our spatial boundaries. So let's read in a shapefile for the administrative boundaries in Uttar Pradesh. Now remember, we've worked with administrative boundaries previously, but those were level 2 boundaries. So level 2 boundaries are district boundaries. But now we want to work at a slightly finer level. So we'll use level 3 spatial boundaries, which are subdivisional or sub-district level. So they're something like within a district, there are subdivisions, administrative subdivisions, and we'll be working at that level. So we will aggregate all of our data to the sub-district level. Okay, so now that we've read in the shapefile, let's subset it because we don't want, so if we plot the shapefile, let me just plot it and show you. So we've called it UP state, but if we plot it, we see that it's actually, let's see what we get. It's actually all of India, but that's not what we want. So let's subset it only to include UP, and the way we do that is we use the name1 variable. The name1 variable contains the names of the states. So whatever state you want, you can subset it using this variable. I hope this syntax is familiar to you, how to subset a data frame. So we only want the polygons where the state is called Uttar Pradesh. So let's do that. And then let's plot it again. And that's much better. So now we only have the boundaries for Uttar Pradesh. And so these are the sub-district administrative units. We will aggregate all our data, the groundwater level, rainfall, temperature, cropping. We will add up the wells within each of these units and take the average. So we'll be working with means that are aggregated to the sub-district level. And so we won't work with the data as it is. We will perform an extra step to spatially aggregate the data. And the way you spatially aggregate data is using a command called aggregate. This is a new command which we haven't seen so far. So it would help if you could pause the video right now and then read the help file for this command, which is done by using the question mark. So aggregation of spatial objects. So what it does is it takes the data, which is point data. So remember, we have data at wells, which are individual points. So for a well, we have the groundwater level at that well, right? How deep was the water level at that particular well? We have the rainfall that occurred around that well in some neighborhood. I've prepared this data. I'm not going to get into how I prepared it. But we have the rainfall that occurred in, let's say, a 1 to 4 kilometer radius of that well. We have the temperature from 2 meters from the surface of the earth, so that the sort of the air temperature around that well, the mean temperature in the months of April and May, so to get a sense of how hot the summer was, because if it's hotter, then wells dry up and water levels fall, and similarly, if there's more rain, then water levels rise. And we want to understand these relationships through a spatial regression. And then, of course, cropping. So how much cropping occurred, what percentage of the area in the neighborhood of the well was used for cropping. So if it's a high percentage, then that well is probably in like a rural area where there's a lot of cropping going on. If it's a low percentage, then it's maybe in an area which is urban, where less cropping, or industrial, or maybe in a forest, somewhere close to a road, but there's less cropping going on. So that gives you a sense of how much water was extracted by farmers around that well, because if you extract a lot of water around a well, then the water level at that well will go down. So we have these three variables, and we have these data at individual points. So it's a point data set, right? But we don't want a point data set. We want to aggregate these individual well observations in a particular sub-district. So if I have a sub-district, let's say Agra subdivision, and I have 10 wells, then I want to take the average of all those wells and just compute one value for the whole sub-district. So that's what I'm doing here using this command, aggregate. And the first parameter is our regression data that we just loaded. Remember, we turned it into a spatial data set. So this will, if you pass it a spatial data frame, aggregate will perform a spatial aggregation. And then we pass in the polygon boundaries that will be used for aggregation. And these are the boundaries. So we want to aggregate this data, which is point data for individual wells, which are at these spatial coordinates, onto these boundaries, right? So let me just show you, let me try and show you a map of both of those together, right? So let me show you a map of both of those together. This is just some live coding here. So let's say we do this, right? Okay, so now we want to also show the wells on top of this. And then, let's see. Okay, so that's the data set. However, the points are way too big, so we maybe make them a little smaller, maybe even smaller, maybe even smaller. Okay, so let me just zoom that in for you. So we have UP and we have data at these point locations. So what we're going to do with this aggregate function is that we're going to go into every sub-district, take all of the wells, add up all of the data, variable by variable, and then take the average. So we will compute an average post-monsoon level for this sub-district. Then for this sub-district, also the average rainfall, the average temperature, and the average percentage of cropped area. And we will do this for every sub-district. Of course, we're not going to do it, R will do it for us, but just to show you that that's actually what we're doing when we run this aggregate command. Please pause the video, go back and watch it again if that wasn't clear. Repeat it as many times as you feel comfortable. I'm going to assume that you understand what aggregate does. So here I'm giving a function which is the mean because I want the average. I could also ask for the sum or the maximum, but I want the mean. And na.rm equals true basically tells R to ignore missing values. So some data will be missing and we want to ignore it. So let's run this. So I get some error saying, so I need to, so spatial data has a projection system, which I cannot teach you right now in the interest of time, because you could have an entire sub-course on projection systems. But the idea is if you want to aggregate points over a polygon spatial data, then two of them must have the same projection system. So let me do that. Let me set the projection of the points to the projection of the polygons, and then that gets rid of that, and now aggregate. So that seemed to go well. And also, so for the percentage cropped area, I don't actually have a percentage, I have a proportion. So I have things like 0.2, 0.4. So I'm just going to multiply that by 100 just so that it is truly a percentage. Now let's plot, let's see how that went. So let's plot our post-monsoon value. Yeah, so now we don't have values over individual wells, we have values over entire sub-districts. So we have a value over this sub-district, this one, and this has been obtained by averaging over individual wells. So you can see the darker orange colors, these areas have maybe deeper groundwater levels, so maybe this is a depletion sort of hotspot. This area borders, it's around Agra, but it borders on Rajasthan. So in this area, there's really we expect that there's not a lot of rainfall because it borders on Rajasthan, which is an arid desert area. So maybe that's why groundwater levels are not so good here. Then up here, we have a lot of sugarcane farming. And then these darker yellow regions have slightly deeper groundwater levels, and the lighter yellow, the groundwater levels are a little shallower, the water is closer to the earth, the surface, the ground surface. So this gives us a sense of the spatial distribution of groundwater levels. So let's look at rainfall. And we see that that rainfall clearly shows a trend from west to east, right? So the western part, which borders on Rajasthan, is kind of dry, so there's not a lot of rain. As you go closer to the eastern parts, nearer the mountains and nearer, Bihar and those areas, West Bengal, you get more and more rain. And clearly, like right along the foothills of the mountains, you get a lot of rain. And then as you come down into the plains and go into the desert, so it's a very, very clear sort of trend that we see. So we do expect that groundwater levels in the western half to be maybe, groundwater level to be kind of deeper because there's less rainfall. That's something that we expect. And let's look at temperature. So you can look at each of these and try to develop some theories, right? So temperature has a south to north gradient. And we know that the northern parts of India are much colder, southern parts are warmer, and we see that across UP being that trend manifesting across UP as well. Right here, when you're getting into Uttarakhand, it's quite cold. And then down here, when you're getting into MP and down here into Bihar, etc., it's much hotter. And similarly, you can look at cropping. So cropping clearly is more in western UP. There's more cropping going on area-wise. And then here in the south, maybe a little more, and then some parts of northeast UP. These are rice districts, a lot of rice cropping. So now that's all good. We've examined our data, we've aggregated it. But now we want to build a weights matrix, right? So how are we going to do that? We want to build the weights matrix and also get a visual sense of what it looks like. So the way to do that is using the spdep package, which we've already installed. So the first command is, we have our spatial data, which is called UP level 3 spatial data. So we use a command called poly to NB, which stands for polygon to neighborhood. So it takes a set of polygons and gives you the neighborhood relationships. So what is a neighborhood? If, for example, this district here, sub-district, borders this district and this one and this one and this one and this one. So any district that it shares some edge with or some vertex with, that's a neighbor. That's what we define as a neighbor. So for each sub-district, we want a list of all the neighbors, and we want to organize it in a matrix form. And R does this for us. So we run the command poly to NB first, and then we get the centroids of each of the sub-districts. And then we can plot the neighborhood relationships. And we can see, so we can go into each sub-district. So we can see this sub-district is connected to all of those around it. And this one is connected to all of those around it. And this is called a queen neighborhood pattern, because even if you share a corner with another sub-district, you're counted as a neighbor. There's other kinds of topologies that you can consider, but this is the most commonly used one. We'll stick with this one for now. So this is fairly easy to understand, right? So this sub-district right here only neighbors this one. So there's only one edge. This one neighbor only has one. This one has two neighbors, one to the north and one to the south. And then most of these sub-districts are kind of connected to all of those around it, which is why we see this web-like pattern. And then we have to do one last step. We want to convert the data format from one type to another. Don't worry too much about this. Basically, this is just a data conversion. Nothing is happening. We're just converting the same information to another data format, because later we need it as a list and not as this neighbor. So we'll do that, and we'll stop here for this session. That's all we're going to do. So just to summarize, what did we do? We prepared spatial data to run spatial regressions. And then we used this spatial data. And the preparation of the spatial data was many operations: loading the data, converting it into spatial data, then aggregating it, plotting it, and looking at the various variables. And then we built a weights matrix to encode the neighborhood relationship. And then we visualized that relationship just to see that everything turned out well. Now we're set. We have all the information, all the variables and the data in place to actually start running our spatial regressions, which we will do in the next session. I encourage you to review this material thoroughly so that both you and I are ready for the next session. I will see you there. Thank you so much for your attention.